So, good morning. As I say, I'm Julian Rimoli. I'm a professor here at Georgia, an assistant professor here at Georgia Tech in the area of aerospace structures. So, I'm going to give you today like a brief introduction to aerospace structures, just to give you a flavor. So, all the things we're going to discuss here, you're going to see more details in more advanced courses. But then I'm going to introduce some basics about structural design for truss structures. And we're going to have that hands-on activity where you will be able to try lots of different designs and see how they work. So, you know, if you're an aerospace student, at some point someone should have shown this picture to you. It's the ideal plane according to the group and your specialty, right? So everyone will try to emphasize their specialty. You know, if you see the production people would like to have a plane where you just nail a wing to the fuselage and that's it. Or the aerodynamics people would like to have a very streamlined plane, you know. So there's this discussion going on. You know that aerospace is actually multidisciplinary. I don't know why why we are having this discussion. Because this is obviously the best plane ever. This is what I do. Alright? So I do structures. I do heavy planes that don't break. Alright, so what is a structure? So the structure is basically, that was a joke. The structure is basically what holds the plane together, or the spacecraft together. In an airplane, you want to have as much as you can be in a structure, in the sense that you don't want to have superfluous weight. So anything that is adding weight, somehow you want it to be also to add strength to your plane. Okay? But people have been studying structures for a very long time, right? So since the Romans invented the arc, you know, the compression arc, where they build these aqueducts. You can go, you know, over the ages, and structures were getting better and better, and you see like the higher and higher buildings, mostly motivated by civil construction, right? And when we, after like since the beginning of last century, the early 1900s, when we developed the aircraft structures pose a different kind of challenge because they have to be strong, they have to have strength, but at the same time they have to be as light as possible. All right? So that's a mission of a person working in designing an aerospace structure. You have to make a strong structure that is as light as possible, because if it is too heavy, first, it may not fly at all. Or second, even if it flies, you know, if you have like superfluous weight that you don't need there, right, it's less payload that you have. Okay? But the problem we have with that is actually kind of nature plays us a trick, a bad trick. In this plot, what you can see is more or less all materials that are known to humankind. And in this axis, we have the density. So basically, in this direction, it means it's heavy. And in this axis, we have strength. So in this direction means the material is strong. And when we see there is kind of like a trend here, so usually stronger materials are heavier. Okay? So ideally, we would like to have material that is in this region, but that doesn't exist. I mean, we are trying to push the envelope through research, trying to go in this direction, right? And that's what I do for my research activities. Try to design a material at the lower scales to give it strength while keeping it light. But more or less the story is like this. We can push the envelope in this direction, but there's not much that we can really do. So what we have to do as structural engineers is kind of like try to understand how materials fail to optimize the deployment within the structure in such a way that each material is working at their optimum. Okay? And that can be understood in terms of stresses. So there is a quantity that has the same units as stresses that you are used to, is pressure. So stress is force per unit area. It's more complicated than pressure because pressure is generally just normal to the surface. So if you have, I put my hand here and push in that direction, right? So the pressure is, the force that is generating that pressure is always normal to the surface. Whereas for stresses, the force could be tangential too. So we can apply a force to this board like in this direction. So we are creating a pressure, but also a component that will have the same units of force per unit area that will be tangential. So stress is a little bit more complicated, but that concept of force per unit area gives you the idea. Okay? And most loading members in structures can be understood in terms of these 5 loading scenarios. So one is tension, where you have your specimen and you just pull it. Okay? The other is compression, where you have your specimen and you just push it to the ends. Then you have torsion. Okay? And each of these states generates different kinds of stresses. Torsion, where you just twist your rod, for example. Then shear. Shear is a little more complicated. So you may have like one plate and another plate joined by the rivet. So you push one in one direction and the other in the other direction. So if you look at the force that the plate is doing on the rivet, on one side is going one direction, and then all of a sudden when you change from one plate to the other, it's going in the opposite direction. So it's generating this shear force. Okay? And then you have kind of composed loading scenarios where you have bending. So when you have bending, you have a beam, for example, you just bend at the ends, okay? And bending generates a complex stress state. In some parts of the beam is going to be tension, and some parts is going to be compression. For example, if I have a beam, and I put two little notches, and I'm going to bend the beam like this. But I ask you, before I bend the beam, where would you put your finger? The top notch or the bottom notch? And I'm bending the beam like this. Where would you put it? Top. Top. So everyone knows top. Why? Because if you put in the bottom, it's going to compress your finger. So at the bottom, the beam will be under compression, right? And at the top, the beam will be under tension. Okay, so you can even understand bending in terms of tension and compression, but now that is distributed within the beam. Okay? And some materials behave differently under certain stresses than others. For example, if you have ceramics that we use for thermal barrier coatings in the discs in the hot area of turbines, for example, you cover this material with ceramics so they don't get that hot, right? So those ceramics are usually really good under compression. Okay? But if you apply like a tensile load, they will just break apart. Okay? So, trying to think in this concept, aerospace engineers have developed and aerospace structures have evolved over the last 100 years to three main kind of structures. So the main structures you will find in any aerospace application, from aircraft to spacecraft, are trusses, where are just slender bars joined together at these places that are called joints. Okay? And those are really efficient, but it's very limited the kind of shape you can achieve, but are very efficient regarding strength and weight. Then, usually this started with the wooden planes originally, and we keep using them today a lot, and we will discuss some applications later. But as we started using aluminum, for example, for building aircraft, people developed the monocoque or single shell kind of structures, where you have basically these formers that give the shape of your fuselage, let's say, and then you cover your fuselage with this skin. And this skin will work for under shear, for example. It will be very good for the torsion of the fuselage. And one limitation of this kind of structure, it doesn't scale that well when you go in size very large. Because what happens, let's think that now this is a fuselage and you're maneuvering your plane, so we have some bending itself. It's probably the tail is pushing one way, the wings are pushing another way, so this may tend to bend. So the parts that are under compression, now just imagine you have a thin sheet, and now this distance is becoming larger and larger. So you have a thin sheet of material. The part that is under tension, you just pull it, and it's fine. But the part that is under compression, what happens when you compress this thin sheet? Yeah. What will happen? Comes out, right? It doesn't take any load. This is called buckling. Okay? So as the structure becomes larger and larger, for monocoques, the kind of structures, the shell will start to buckle under compression. So you can put some aids to that to prevent the buckling of the shells, and this is what we call the semi-monocoque structures, where on top of these formers, we are also adding longerons that go across the entire direction, the entire length of the fuselage or the wing or whatever structure you're talking. And you may have also some stringers probably next to windows and stuff like that. Okay? So you can see how the structures evolve in different ways. But I said that, and each of them has their own advantages and disadvantages. Today what we're going to discuss in our activity, in particular, is truss structures, the first kind. And don't be fooled. They are simple, but they are everywhere. Right? Sometimes the simple solution is the best solution for many problems. And here I'm showcasing some scenarios. So this is the Morpheus moon lander that is being developed right now at the NASA in Houston. Okay, you can see that all the landing gear structure is truss structure, so these bars joined together. And this is another aerospace application, another space application. This is the S3, S4 truss in the space station, this guy over here. So the main structure of the space station is all trusses. Okay? And you can see even what they are using here on Earth to hold it is a truss. all right? And then even within a plane, so you know, inside the wing, you have like these big beams for holding the bending that are called the wing spars. So those beams could also be trusses. In many cases, they are trusses, particularly for like general aviation purposes. And even the ribs that are the ones that give the shape of the wing and carry the vertical load on the transfer from the aerodynamics load to the main structure of the plane are also made of trusses. So trusses are very, very important. And the nice thing about trusses is that they could be understood only in terms of tension and compression. Okay. So the formal definition of a truss. So a truss is a structure that is composed of slender bars that are joined together. Okay. And they have to be joined together at the same point. So basically the center points of each bar, the center lines of each bar has to intersect at a single point. If that happens, then we could idealize the structure as if they were joined by pins. Okay? And that has a big implication that I'm going to discuss right now. But the other thing that is important for trusses is that either the support could be the support for a bridge, but could also be the support of a wing into the main structure of the fuselage. Either the supports and the loads have to be applied at those pins. Alright? So basically, let's say this is a wing spar. Goes very long. Can you see? Try this. So eventually, statistically, one has to work. Yeah. So let's say this is a structure in a wing spar. So you have to, it's a truss structure. So you have to pick the point to attach the engine on the wing. Okay, so you will attach the engine, let's say here and here. You will never attach the engine here, because if you put a weight here, this guy will start like bending and no longer works as a truss. Okay, so this is not designed for carrying load at the center point. It's always designed for carrying loads at the end points. The same for the supports. If we want to attach this to the wing, we're going to put support points here and here. All right, and here we have like a to the fuselage, sorry, you will have the fuselage structure, for example. Okay, so what happens? Why is that important? Because if we have now if you look at every component of your truss, each bar of the truss, now they're connected through the ends, and all those, everything is happening at the pins, okay? So it doesn't see any force in here. So you may have one force here and another force there, right? But we know, for any body from physics, that to be in equilibrium, the sum of forces acting on the body has to be equal to what? Zero, right? And the same applies to any subpart of the body. So we can look at the structure as a whole, but we could also look at each bar on this truss as a body in equilibrium, all right? And now we know that this body has forces only at the ends. So it only can have two forces applied. Right, or two resultants. Could be more forces, but at the end of the day, it can be reduced to one force at one pin, one force at another pin. So this force at these two pins, so for the sum to be equal to zero, they have to be what? Equal and opposite. Because otherwise, the sum of forces will not be zero. So if I have this guy over there, over here, I will have to have that guy. Right? So they have to be equal and opposite for the sum of forces to be equal to zero. Right? But then there is another equation of equilibrium. I don't know if you saw it, but I can tell you intuitively, sum of moments equal to zero, which means that this thing does, you don't want this structure to rotate, okay? So if you see, if we have a bar like this and we apply forces like this, what's going to happen? It's going to rotate clockwise or counterclockwise in this case? Counterclockwise, right? So you get that intuition. So the only way for this not to rotate is that these forces are equal and opposite, but also along the line of the direction of the bar. Right? So there could be either like that, so now this thing will be in equilibrium and will not rotate, or could be the other way around. So in this case we have the bar under tension, and in the other case we have the bar under compression. So when we have a truss structure, all the members that make up that structure are either under tension or compression or no load at all. Alright? So a whole structure can be understood only in terms of those two states. Okay? And what happens, this is the last slide before starting our activity. What happens is that bars fail in a very different manner if they are under tension than if they are under compression. So we are assuming these bars are slender now, so it's not like a really bulky bar, are really slender bars like the ones you saw in your drawings. So the bars we discussed, to be in equilibrium, there will be either under tension or compression. Now if we do an experiment and we start loading a bar, we start pulling a bar, it will take a lot of load, right? It will take a lot of load, and if it is made out of metal, at some point it will plastify, which means it will start yielding. It will start yielding, will take not much more load. This is an ideal case, this is called ideal plasticity, elastic ideal plastic. So this could go more like this also. But conceptually is that you don't take much more load, but you can still afford to deform. And then at some point you just break. Okay? Now if we do the same experiment with a slender bar and we push it, what happens? And take a lot of load, then you have a very thin bar and you push it at the end. How do you expect this to fail? Yes? Will buckle. So I always go to the extreme case. You know, a very slender bar is a cable. Okay? You know that you can pull a cable as much as you want, but the moment you push at the ends, it just goes out. Okay? And the thing with, there is a formula for that to tell you how much load a cable can take or a bar can take under compression. So under tension is just the area, the cross-sectional area of the bar, times this characteristic material property that is called the yield strength. Okay? So this guy is usually very high. So you basically under tension, this is fixed, this is material property, but you increase the area of your bar and you can take more and more load. Of course your structure will become heavier and heavier, so there is always a delicate balance. But you know it's pretty straightforward. There's one variable for you to control if you have your material fixed. It's increasing the cross-sectional area of your bar. Now, if we are under compression, this critical load or buckling load is given by this formula that eventually you will learn where this comes from, but intuitively we can discuss today. So E is a material property, so you cannot touch. And then pi is 3.14, whatever. And I is a property of your cross-section of your bar that is related to how far the area is from the center of the bar. So let's say you have a bar that looks like this. It's some sort of measure of how far this area here is from the center line of your bar. Okay, so this bar is going like this, very long, right? But for this class, if we keep the geometry constant, we can assume that this is somehow related also to the cross-sectional area of your bar. Okay, so if you make the bar wider in general, you increase this guy. Okay, it's not the area, and you will learn what it is later, but intuitively, you know, and that's why people usually in civil construction they do the I-beams. So they do the I-beams, right? So you have like this area far away from the center, so you are increasing this guy I. Okay, and if you make your I-beam taller and taller, this thing keeps increasing. So one way is making the bar kind of bulkier, if you want, right? So basically, if you have this bar, it buckles, let's say, under this load, and now we make the bar like this, higher, you will probably not buckle. Okay? So, and you can see intuitively how that works. The other thing, and it's very, very important, has a major impact because it's to the square, is the length of the bar. Okay? So eventually, if you make your bar long enough, you are increasing L, you know, and in a quadratic fashion. So you are decreasing the load like, by a large amount. Okay? So now you may have this bar, let's say you have this bar that does not buckle, and now you have this bar, the same cross-section, and it does buckle. So the longer the bar, the more prone it is to buckle. Okay? So the lessons from here is the following. We are going to see now with hands-on activity. Is that when you have a bar that is under tension, the way you gain strength is just by increasing its cross-sectional area. Okay? But when you have a bar under compression, there are two tricks. One, you could increase the height of the bar, or this moment of inertia of the bar, that we call it. Okay, you could think of it as the area, but you can also decrease the length. Okay, so you have two ways to tweak your structure, and we're going to see how to apply that now on an activity. So what I want to do is the following. So now we're going to have a group of two. So just join like this, join like this, join like this, and you over there